Welcome back to part 2. So let's look at example 9. This video will be much shorter because I've only got 2 examples. So this example, we are not able to rewrite like we did up here and work any other way. So I need to write this so that it's as a power function. So I'm going to rewrite it as x cubed plus 2 to the 1/2. Now I can take the derivative because now it has the power and I can apply that power rule. So the derivative of function g would then be 1/2 times the coefficient in front. So that's a 1/2 times 1. And then remember, we're treating this whole thing as the big function. So we're going to just rewrite this, and then we reduce that by 1. So 1/2 minus 1 is a negative 1/2. And then we link on to this the derivative of the inner function. So the derivative of x cubed is 3x, reduce that by 1, squared. And the derivative of the 2 is a 0. So I am done there. Now I need to clean this up. This has 3 times a half, x squared, but this negative 1/2 there is going to put that in the denominator. So we're going to have 3x squared over 2 times x cubed plus 2 to the 1/2. I'm going to rewrite that. I think I'm going to write that with the square root. Now that may be an acceptable answer and an acceptable form for your answer if your teacher does not require you to rationalize. If they do require you to rationalize, you need to do that and get rid of that radical in the denominator. So we are going to just practice that. So I would do it by the radical of x cubed plus 2 over the radical of x cubed plus 2. Alright, so I'm not changing the value, I'm just multiplying it by 1. And now that denominator, that radical, is going to go away. Now the numerator is still there, that radical, but that's okay, we're just going to leave it there. Radical of x cubed plus 2 over, but now our radical in the denominator has disappeared and we just have 2 times x cubed plus 2. That is a proper form of your answer. You don't need to distribute the 2 as well down in the denominator. Now, what I'd like you to do is to look at this application problem. So go ahead and pause it and copy that bungee jumper's equation. So you have a bungee jumper and the height from the ground up to the jumper is by this equation. You could tell this is a quadratic, and it's going up, okay, but you're on the ground, so you're looking up at the bungee jumper. I don't know why anybody would do that. Some of you may have. You're not going to find me doing it. All right, I want to know on an interval of 0 to 6, so from 0, it's probably 0 to 6 seconds. Find the minimum and the maximum height of the jumper at that point. We do not know how high they are starting, or do we? You know, look at that equation, you can probably tell. But let's determine what the minimum and the maximum height would be. So in order to do that on that interval, the first thing you're going to do is if you take the derivative of the equation. So when we do that, if we take the derivative of this h equation, that would be 2 times the 20, so that would give us 40, t to the first power, because I've reduced that by 1, minus, this is to the first power, 1 times negative 160 is just negative 160, times t, and I reduce that by 1, so it's gone. The t's are gone, and the derivative of 330 of an integer is 0. So then the second step you're going to do, stick with my colors here, the second step is to get your critical points. And the critical points are the zeros of the derivative. So when we do that, if we set that equal to 0, I've got 0 equals 40t minus 160, and add 160 to the other side, divide by 40, you see that 4 equals your t. So is the second, 4 seconds, is that in your interval? All right, you need to ask yourself, is 4 in the interval that it requests? All right, and yes, this one is. So then the third step would be to evaluate it. And you need to be careful on this because you're evaluating the original function now at those times, not the derivative. So now you are evaluating the function at 0 at the minimum of the interval, at our critical value of 4, and at the other end of the interval of 6. All right, and you can do that several different ways. You can put this in y equals and look at the table. You can plug in these values. Now the 0 we can do right now. If t is 0, then we know we're at 330 feet. If t is 4, as I said, you can do this in the calculator with the table, or you can evaluate it yourself. But you will find that if you evaluate that at 4, it's 10 feet. If you evaluate it at 6, it's back up to 90 feet. Right? Because the bungee jumper has starts up at the top at 350 feet, goes down in 4 seconds, they're at 10 feet above the ground, and then they're going back up in 6 seconds, they're back up to 90 feet. But you can tell only obviously from where you start at 0, and in that interval at 4 seconds. Right, so that's for derivative.